Today is 11th of October and we are into shear stresses of beams. We have finished bending stresses in beams, but uh, as we know that a structure transversely loaded will have both shear and bending stresses. So we have learned about the bending stress, we have learned how to calculate bending stress, we have learned about the flexor formula or the bending formula. Today we are going to develop shear stress formula. Before we start, let me uh, wish you all happy Navratri, and today is the 6th, we call it Sosti, and happy Sosti to all of you. Okay, um, I showed you one, demonstration in the last class, right? Where these parts are already covered, so I'll not cover these things. Where I took an I section, right? Right. I took an I section which was like this. Should be symmetric, okay? Cannot be asymmetric. It can be if by design, but generally we make it symmetric. I section. And then what we did is when I bend it, by my hand, you saw that the I section was it got uh, detached at the top portion here, right? The joining portion. The glue was not working. Our glue was become inactive, and therefore it was detached from here, right? And I say the detachment is because of shear stress. Today we are going to discuss why it is because of shear stress. Okay, so if you have a bunch of pages in your hand or a notebook in your hand, you can just easily see a demonstration if you want to, right? The demonstration will show that if you bend the book or the notebook that you have in your hand, you will see the pages are actually not aligned together. They will depart from each other, and those depart is due to shear stress acting between the layers of the pages. Okay, all right. So if you want to see the demonstration, I can show you with a small video here. You can see the better video in websites in YouTube. I hope all of you can see me. Can you pin to me? Let me also pin me yourself, otherwise how do I pin myself? Yeah, good. So you see this book, right? And you see the pages here. All right. So as you assume this portion to be a beam. So this is a beam. It's supported maybe here and here. So this is a beam, and when you bend the beam, you see here at this end, the pages are going apart from each other. The more you bend, you'll see the more the pages going apart from each other. Here at this end, since they're fixed, it doesn't happen here, but it happens here. They will start going out from each other. The reason being that each of the layer, when you bend it, each of the layer tries to move apart, right? So we said that each of the layer gets strained, right? And when each of the layer gets strained, they try to hold on to the other layer, or they're up on the top or in the bottom. And when they go out from each of the layer, they put a shear stress on those layers, the layer above and the layer bottom below, right? So, all right, we're back to our class notes. So we are going to see that today through theory. So what we are going to look into, we are going to look into shear stress due to Euler-Bernoulli beams and not due to deep beams. Okay, so not due to deep beams. So when I say Euler-Bernoulli beam, I mean the length, sorry, the depth to breadth ratio is not very high. So when I say Euler-Bernoulli beam, B is nearly equal to D. Lesser, but nearly equal to. B is always lesser than D, but not very less. So if your B is around 150, your D can be 250, right? It cannot be 450, something like that. So between 1.5 and 2 should be okay. All right. So that's what we understand by Euler boundary beams. Now let's look at this. So this is what I was demonstrating. When you have a beam like this, you know, and you load the beam with some load P here, 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 and once you give a load, it will have a shear stress, a shear distribution, right? You know that SFD will come into picture. When you have this SFD, what does SFD do? The SFD is trying to cut the structure from that location, right? Every SFD that you saw, so let's say I have a beam like this, and I put load here. So my SFD diagram is going to be something like this, right? This is my SFD. Which unit is in mm? Yeah, these are in mm, yes. Okay, so when you have this kind of shear stresses, what does shear force do? The shear force trying to, whatever shear force you have here, will try to cut the beam here. They will try to break the beam there into two parts, like a scissor cut. It will try to do a scissor cut. So if you take a section here, the section will show, since this is, let's take section here, since this is the positive part, the section here will show a shear on this side like this, and the section there on the other side will show us here like this. So that means you're trying to cut like a scissor, okay, into two halves of the beam. So if I have this surface, if I take this surface here and show that surface in this picture, right? So the shear force is going to graze through the surface, right? Like this. It is going to graze through the surface like this. Okay. Now, if you have a very small, if you take a very small section out of it, very small section. So what you're looking at a very small element here, and then you're extended that element all through the width of the beam. If you take that very small, and then you draw this here, you will see that there is a shear stress that is acting here like this, downward. Okay. And this seems to be a square element, right? So if that is a square element and there is a shear acting here, so if you look from this side, okay, there is a shear acting here downward, and therefore there will be a complementary shear which will be acting here, cross shear, not complement, cross shear, right? So this cross shear will be acting here. So therefore you will see shears acting here. For all these shears, the similar shear stress will act here with the same value tau, but the direction is that way. And therefore this layer is a shear stress like this here, and the above layer will have a separate shear stress, right, opposite to this. And then there will be a difference in shear, and then they will try to detach from each other. That's what you see in books or the I section that I've shown you that day. So this stress is called shear stress in the beam. It acts on this surface as well as between layers here. Okay, so they act both way. All right. So having said that as a shear stress, let's go ahead. This is what it has been shown here. You can see and written in greater depth. So vertical shear stresses must also. So now this surface, there is no shear stress acting at this surface, right? There is no force that is acting on the surface that is grazing to the surface. There are forces that are acting this way, right? Normal forces, transverse forces. But there is no force that acts on the surface. like this. Therefore, at the free surface from on the top as well as the bottom, your shear stress is going to be equal to 0 because there is no external shear stress acting on the surface. The vertical shear stress will start 0 here as well as 0 here, end in 0 here because there is no shear stress at the boundaries. And this layer of shear stress will also be 0 at the top layer, like here. Here, it will be 0 here on the top layer. But immediately layer after it will have some value based on the vertical shear stress. Okay. So top shear stress, so vertical shear stresses must vanish at these locations, the top locations. Okay. And this is the shear stress diagram of an element that you take here. This M element is this. Okay. Now, how do you calculate that? So this is what I have shown. I've shown last class through the uh, T section or I section. Now, if you have many of these, let's say I have a section made up of many such layers of beams. What happened? Why it's not writing? Yeah, like this, right? So when you put a load and when there is a shear stress into it, it will behave like this. The next layer will go a little bit beyond that, right? Like that, it will start, bending from each other. And this is what creates the shear stress. This is the effect of the shear stress. Now, how do you calculate it? So we use the calculation the same way that we did earlier. So let's take this beam. So this is a simply supported beam, okay, with a load here, okay, and you take any cross section here, right? A cross section I take which is tx distant apart. So one is mn, the other one is m1 n1. Okay, one is mn. So if I draw it in a 2D picture, this is your mn and this is your m1 n1, and they are dx distance apart. Okay. Now, on the left of the section, on the right of the section, we have to balance the moment. Since there is a load acting, the moment is not going to be constant. Neither the shear force is going to be constant in a general case. So you will have M here on this part of the section. So if I show this section, I will have a M here. I will have a V here, vertical shear force. Similarly, here there will be a vertical shear force, which will be V plus dV, and there will be a moment which will be M plus dm. So remember the directions considered on the element are positive directions. They are not opposite to any conditions that we have. Okay. Now the same section, if I show here, I know there is a bending stress acting, and we know how the bending stress act. So this is the section here. That is the section here. The bending stress that is going to act here is going to be like this, and the bending stress that is going to act here is going to be like this, right? Both are the same. Remember that on this side, it's going to be compressive on the top. So like that, it will go. On the bottom, it is going to be tensile. So it is going to be like this. And here it is going to be like this. Whereas this is compressive. And the value will increase linearly from neural axis to the top. Okay. This side of the sigma is going to be sigma 1, let's say, and that is minus my by I. Whereas this side of the sigma or the normal stress, which we call sigma 2, let's will be given by, this is the moment, right? M plus dm. So m plus dm y by I. Okay, is that clear? So what I'm doing here, I'll repeat again. What I'm doing is we take a beam section, right? We take a beam and then take a section, two sections, which are dx distance apart. One is at mn and one is at m1 n1. So if you want to see the picture better, this is a 2D picture of the beam. Okay, and this is your m1 mn and this is your m1 n1. Note the moments, if you take the sections apart, right, the moments that are going to act on it are going to be different. So if I draw it like this, So this side is going to be M with the vertical shear force B. This side it will be downward shear force V plus dV and a moment M plus dm. This is your M, M1, in N1, okay? And this distance is Tx, right? So now that if I draw, so since there is a moment acting on this surface, M, there will be shear stress acting on that surface. The shear stress, sorry, normal stresses will be acting on the surface. We have defined the bending stress or normal stress, and that's going to be looking like this, right? On the top part, since it's the positive everything and the loading is downward, top part will be compressive. So the loads, the stresses will be acting with an arrow inside the material. Similarly, on the bottom part, there will be tensile. So it is like going this way, okay? And on the other side, on the right side of the element here, you will have downward V force and a moment. Now this moment is M plus dm. So M plus dm will create again a normal stress or the bending stress, and they will look like this. So the sigma 2 acting here is going to be minus M plus dm y by I, whereas sigma 1 acting on the left part of the section is going to be my by I. Where do you know M is the moment acting at the section, I is the second moment of area, and y is its distance from the neutral axis. Okay. Now, if I take a portion of this, and look at the force balance at that portion. So if I take only a portion of it, this portion of it, okay? If I take this portion of it and take force balance, what are going to look like? So this portion is coming here. Okay, the portion is taken at a distance y1 from the neutral axis to the top. So this portion is y1 to top. Okay, so it is y1 to h by 2. So this top is h by 2 from the neutral axis, and it starts at y1 from the neutral axis, right? If I look at the sigma 1 stress, that's going to be a trapezoidal like this. If you want to see that picture, it's like that, right? So same thing, you have just cut it from here. So this is the portion you're going to see. So that's your compressive force on the left side. Similarly, on the right side, you will see something like that, right? Another trapezoid. So right side, you have another trapezoid, sigma 2, acting on the right side. Okay, and this is above the neutral axis, so it's going to be compressive. Now, since you have taken an element out of this, right, you have separated this portion from the top portion. Now, these two layers, as we have discussed, where there were shear stresses in between. So there is a shear stress that is going to act in between, that is called tau. Let's call it tau. Okay. All right. Now, if you look at the force balance on the right picture, the force balance, so this stress will create a force on this part of the element. So this face will have some force due to these stresses. Let's call it F1. Similarly, this face will have some stresses because of some force because of these stresses acting on it. Let's call it F2. And this shear, which will be acting on the area like this, will create another force. Let's call it F3. And the top surface, there is no force because top surface is free of force, right? There is no shear acting on the top surface. Okay, so that's not going to be any force there. So it's not there. So you have F4 equal to 0. So you have F1, F2, and F3. And if you do balance of force, it's going to be F1 plus F3 is equal to F2. So F1 plus F3 is equal to F2. So that's the element will be in equilibrium because everything is in equilibrium. So that element also has to be a part of the beam. So it has to be in equilibrium. Therefore, F1 plus F2 is going to be equal to F3. Now, if I do that, okay, this is what we are discussing right now. Now, what is F1? F1 is the integration of the stress over the area there, right? Over this area that you have here. integration of the stress over that area. Similarly, F2 is integration of this stress, sigma 2, over this area. So F1 is going to be sigma 1 dA integral over that area, right? And F2 is going to be sigma 2, because it is acting on the right side, sigma 2 dA over that area. Now, what is sigma 1? M1 by I, My by I. What is sigma 2? M plus dmy by I. Okay, clear? Now, F3, this force is result of these two subtraction of these two forces. So F3 is equal to F2 minus F1. And that if I have to do, I have to write F3 is this minus F1 is this. So what will happen? It's integral in the same area because this area is not changing, right? So this y distance is same, it's not changing, and therefore I can put them together. Mi into y cancels with this my into I. So you end up having only integral dm y by I into dA. All right. We end up having dm y by I into dA. Right. Now change in moment between the section. Change in moment between the section doesn't depend on this area, right? That will depend on this dx, but not this area. Change in moment. And therefore, that can come out. Dm and I is a constant in the cross section. So that also comes out. So dm by I comes out. It becomes integral y dA. Now this is F3. F3 is going to be equal to force stress into the area. Now area is, if I assume the depth to be, the width to be b, that means this side it is b, right? So it's going to be, this is dx, it's going to be tau b into dx, F3. Now if F3 is tau b into dx, I can write that here. So tau is going to be dm by dx 1 by ib, that b has come in the denominator, the dx has come into the denominator, integral y dA. What is dm by dx? We know dm by dx is the shear force. Derivative of moment with respect to x gives you shear force. So dm by dx is shear force, is going to be v. So this is v by ib. And now there is an integral here, y dA, which is the first moment of area. We name it as q, first moment of area. Which area? First moment of this area. Okay, with respect to what? With respect to the neutral axis. So first moment of area, this is the shear stress formula, tau equal to vq by ib. So you have to always remember this formula. You cannot forget this formula. It's called vq by ib, where v is the shear stress, or shear force acting at the cross section. I is the second moment of area. B is the width, and Q is the first moment of area above the section that we're considering. Okay, that's how it is calculated. Is that clear? How do we calculate Q? Is an important question that we have to solve, in while dealing with shear stresses. Okay, so let's look at beam. This is a beam again, a beam, simply supported beam with a payload acting here, right? And the beam will have, what do I say? Beam will have moment and shear force distribution, bending moment and shear force distribution internal. Due to the shear force, we will have shear stresses. Now let's look at a layer where we want to calculate the shear stress. Let's say I want to calculate the shear stress at this layer, at this location, and that location is at a distance y1 from the neutral axis. Okay, so this is the picture that is shown here. That's width b. So this is around this. So what you do, you take a section here and see what is the shear force acting here, the v. Calculate the v, and when you take a section here, that section is drawn here. Okay, now your height or the depth of the beam is h, so each distance from the neutral axis is going to be h by 2. And when you have that, how do I calculate my q? Because my formula is given vq by ib. I will know v based on my SFD at this location. I and b will be known. I will be, you can calculate I with respect to this neutral axis, bd³ by 12. So that will be known, and b is already known. Now we have to calculate q. Q is integral y dA. Remember that when we developed it, we developed for Q for the section above the section I'm looking at. So we are looking for Q for the section above it. Okay. So it will be between h by 2 and y. So this is what I have to look into. So what is this? Integral of y dA. So it's going to be from y1 to h by 2, y into b into dy, right? What is dA? dA is width is constant b, right? Oh, sorry, here width is constant b, so it is b into dy. dy is a small elemental, you take it here. This is the area. Now if you integrate that, you get b by 2 h square by 4 minus y1 square. So you see this is a variance with respect to y1 square. Okay, so you do this, this is what I have shown. So this is a small elemental length dy, elemental width dy, and b is the width here. So therefore the elemental area is going to be b into dy. So that's what replaced here. Okay, so if you do the integration, you get this. This now can be written in a better format. How is so? If you see this varies, with respect to y1 in a square format. So when y1 is h by 2, so when y1 is the top, h by 2, at that point you replace h by 2 here, so it will be h by 2 whole square. That becomes h square by 4, so it becomes 0. So at the top layer it is 0. Similarly, the bottom layer you can do it because it's square. It doesn't matter whether you are top side or in the bottom side. It's coming out to be 0 again. Okay. So now you can do that. We can do that in a different way. What is the area? First moment of area you have to do, right? So what is the area here in this section? It is, this portion is h by 2 minus y1. So h by 2 minus y1 into the width b. So that's your area. I have to take first moment of area. So I have to look at where is the center of the area going through and then take a moment with respect to my neutral axis. The center of the area, that means this line is going to be y1 plus half of this width. So it is y1 plus h by 2 minus y by 2, right? Half of the width here. This is h by 2 minus y1, half of that. So if you multiply these two, you're going to get b by 2 h squared by 4. So you get same thing that we got through integration here. You get the same thing here. Okay. So it is written here, area above y1 into distance between the centroid of the area and the neutral axis. That's what your Q is. Okay. Right. So now if you multiply it, if you do the integration, you will get a distribution which will be parabolic, 0 here and 0 here and like this. And it is going to be maximum at what point? When y1 is going to be 0, right? The value of Q is going to be maximum when y1 is 0, and maximum Q value will give you maximum tau value. So tau max is for Q max, and that comes out to be y1 needs to be 0, so it comes out to be vh square by 8I or 3b by 2a. Okay, a is h into b. So it is 1.5 times the average shear stress. So what is average shear stress? Average shear stress is total area here is A, right? Your shear force acting here is V on the surface. So average shear stress is going to be V by A, right? But this is 1.5 times than V by A. So your maximum shear stress is more than your average shear stress here in this case in the cross section area. Okay. Now if you draw that, the drawing is going to look like this. So it is 0 here, it is 0 here, and maximum at the center, at the neutral axis, not center, maximum at the neutral axis, and it is varied parabolically, square parabola. So it's going to be like this. Now, if you think the beam is made up of various layers, right? So these are all layers. The shear stress at this point is lesser than shear stress at this point. Okay. And therefore, there will be a shear movement, right? There will be a rotation here. If you take an element like this, there is tau 1 acting here and there is a tau 2 acting here. Therefore, it will shear. And in the top layer, it is 0 in the top, that is fixed there. But in the just below that, it is tau acting. Therefore, it will be again go our rotation. Okay, is that clear, Kanikeswar?
Sir,
So,
I have a doubt, sir.
yes.
Is B inside the plane? Because for F3 it was taken B is inside the plane, inside the paper.
Yeah, inside the paper. It is this way B. This is my length, right?
Sir, then DA is like along the paper, right? Sir, along the XY plane.
Dx is along xy plane.
No, DA.
dA is this one.
So, okay, sir. So, okay.
Is that
Okay, sir.
clear? So I will tell you again. Wait. I'll take a page here and explain. All right. So I have this length of the beam, right? Okay. And we want to look, let's say, at a section here, section A. And when you draw a beam, you have to draw like this. You have to draw the neutral axis. And outside, I will draw something like this. What is this? This is the cross section of the beam. So this is cross section. So this is my length, okay, L, and this is my B, and this is my D. Okay, clear. So that actually is a cross section. That's not part of the length of the beam. It is a cross section of the beam. And that is actually here, this one that is drawn here. Now, this is how you draw. So you show all the dimensions. So we show the length, we show the width, we show the depth, everything we show it. Only thing that is common between them is the neutral axis, because neutral axis passes from the same point. So this length, this is x-axis. So this is your x, but here it is z, and this is your y. This is your y. Okay. So the 3D representation is put in 2D in this format. Now, if I take this A section, right, section A, if I look at section A, what do I get? Cross section of section A. This is my y, and this is my z. Sorry, this is my z. This is my z, and this is my y. Okay, this is a cross section because your shear force is acting all through like this. Right. So that is what we call V. Okay, V. So this is the cross section. Now the same thing I can write here. I can draw here again. I'm drawing this axis. It is not necessary to draw, but I'm drawing it for our sake of understanding. Because if you draw those axes, it becomes more, cluttered picture. So now what we want is we want to find somewhere here the shear stresses, right? Somewhere here we want to find stresses. What is the tau here? So that may be represented by this line, right? Because along the width it is going to act, right? So this is y1 distance, y1. So this is going to be again y1. Now to calculate that, I need to calculate the area above it. So I have to calculate the area above it and its first moment. So this is my q. This is area for q calculation. Q equal to area into center of area to neutral axis distance. Okay. Now when I'm doing dy, my dy is draw that again. Now I'm not drawing this y, this is my zz, and I have here is my y1, right? Okay, so I have to do dy. So I will calculate dy like this. Sorry, dA. Okay, so this is my dA is equal to, this is b, right? This is my b. It's going to be b into dy. That's clear? And then you do an integration. So it's going to be q is equal to integral y dA from where to where? Y1 to top, right? Top is h by 2. So that's going to be y1 to h by 2 y into b into dy. Okay, and that will come out to be same. So this integral will end up in this. Okay, I hope that's now quite understandable. Okay, now let's look at few applications, a few salient
So,
points of this. Yes.
so small confirmation. So like the shear force is present due into balance in normal force, no, sir? Like above it, right? Is that right? Sir? Like
What is
um,
balanced normal force?
I mean, for it to be in equilibrium or something like.
Yes, everything is together, right? Your bending moment, your shear force diagram, everything is, all together. It's not that shear force is acting separately, moment is acting separately. In a section where there is no V, right? When there is no V in a section, you will not get shear stresses. You will get only normal stresses.
Okay, sir.
Okay. Now let's look at few critical points. I want to find shear stresses at and draw the elemental diagram at various locations of the beam. So let's first look at a section here. Okay, some point above the neutral axis, and we know that for a load like this, above neutral axis, that point will be compressive. At that point, what is this? So I have this element. So let's say this element is drawn here. Element is drawn here. Okay. So this is my J point, and this is the element. So I have to draw the elemental shear stresses, right? So there will be shear stress above, shear stress below, and whereas the normal stresses. So let's say this is my tau. Tau here will be acting downward, so this has to go this way. Okay, right? And there will be normal stresses, and we know the top part will be compressive normal stress. So this is going to be this way, and this is going to be this way. So this is my sigma y, or we'll write it as sigma x. Sigma x is equal to m y by I, right? Sigma x equal to, here you see the right side, sigma is equal to my by I, bending stress. The same thing is going to act here. Sigma is equal to sigma x equal to m y by I. What is our tau? Tau is going to be this, which is equal to vq by ib. Okay, and what about this stress? Sigma y is 0 because nothing is acting on the normal upward side, so that's going to be sigma y equal to 0. Now the same element, if it's down one here, let us name it as K for Kanikeswar, K, IJK, so that's K. So now what? Same element, no, same distance at the bottom also, if I have All right. So, and let's say that distance is also y. The diagram is just going to change. Where is my, yeah. So this is going to be now axial tension. So this is my sigma x equal to my by I, right? And this is also sigma x equal to I, and this is going to be 0. And there will be shear stresses, right? No, the shear stress direction doesn't change, it remains same. Tau equal to VQ. Did I draw it correctly? I don't think so I've drawn it correctly. Let me correct my picture because CSS diagram is positive, it's not negative. VQ by IB is positive, not a negative sign. Okay. So it's going to be like this, and like not like this, like this. And it's going to be like this. It's positive. Okay. So it's going to be positive. Okay. VQ by IB. So that's how you draw. Now let's look at two more points. Let's look at two more points. One is at the top layer, just at the top layer. Let's say this is my top layer. This layer, this layer, and this layer. Okay. We have to draw, right? So let us put the names with my students' names. So some of the names, let's say, okay, A, C, okay, G for Ganesh. So let's say this is G. Okay, and then let's say Ace. There are a lot of names with Ace, right? So let us put this as Ace. And the third point as Y. Yes, Venkat. Here is only one cat, Y. Okay, no, Y cannot use. I'm sorry. Yes, and I cannot use Y because Y is used for distance from neutral axis, so that cannot be used. So T, yes, T. I can use T. Let's say T. So at the top point, if I look at G, right, the stresses at G. So this is my element at G. Okay. Now, what is your shear stress at the top G? Now, before shear stress, let us go into normal stresses. First, we draw normal stresses. So what are the normal stress? We know normal stress is going to be, this is my h by 2. So sigma x is going to be m into h by 2 by I. Okay. So that is going to be m into h by 2. And what is I? I is b into h cube by 12, right? B into h cube by 12. And then you can do all the calculations that you need to do, right? You will be happy to do those calculations, and some values will come. That value will be m into h, and h will cancel, bh square here, and 1 by 6, I suppose. Okay.
Into 6, sir.
Into 6, yeah, 6 bh. Okay. Sorry, yeah. 6m by bh square. So that's going to be, and it's going to be compressive in the top. So this is going to be my sigma x equal to 6m square. Same thing here. Sigma x equal to 6m by bh square. Now what about top sigma y equal to 0? Because there is no force. If there is a sigma y here, then the beam will go up, right? So there is no sigma y there. If there is a sigma y here, the beam will go up here because there is no one resisting that. There is no external force acting there, right? So there is no sigma y. Okay, then that is also 0 here. Sigma y equal to 0 here. Now, what about neutral? What about shear stresses? Let's look at shear stress here. Shear stress is going to be V is V at G, right? Let us put at G here. Okay, V at G is going to be V Q by I B. And what is Q? Q is 0 in the top layer, right? Because Y is H by 2. So Q is going to be 0 there. So if
So
Q
that
is
has
0,
to be tau of G, right?
thanks. Tau of G. Right. So that's going to be 0. So there is no shear stress. If you draw it like this, you have to put tau equal to 0, or else you don't draw. Either way. Okay. Now let us look at T. T is going to be same as G,
So
right? Wait a minute. Let me finish these diagrams. T is going to be same as G because it's just mirror point. Only thing is your normal stress is going to be tensile now.
So T, not G.
Yeah. Yes. Thanks for being so attentive. I make a lot of mistakes like this. So this is going to be sigma x equal to, again, sigma m by bh square. Here also sigma x equal to 6m by bh square. This is going to be 0. That's going to be 0. And tau is 0 also, right? Tau t is equal to 0. Okay. Now let's look at S point. Okay. What will happen at S? What is your bending stress at S? Bending stress sigma x is equal to, let me put bar so that
Zero.
it's easy, right? So it's going to be sigma x equal to, good, my by I. What is y at center? It's 0, right? So it's going to be 0. Sigma y equal to 0, and tau vq by ib, and we just calculated for a rectangular section is going to be 3 by 2 v by a, right? So it's going to have only shear, and that's going to look like this. Tau is equal to 3 by 2 v by a. Okay, so that's a complete picture of the beam. Anywhere else you can always find out and say what will be the values. Right? There are a few salient points which are written here. Please go through them. These are the main understanding parts which you have to remember.